This is a pet project using fNIRS to verify the case of brain freeze. Brain freeze is known to give pain in the brain. As I had a chance to try on a portable brain imaging device from a company named OB Lab, I thought it would be fun to utilize this opportunity and see how the brain reacts during a brain freeze. Since the device was able to detect brain activities, I thought it was a perfect fit to experiment. At some point in our lives, we all experience a headache when having cold ice cream or ice drink. This is called a cold stimulus headache, also known as the brain freeze. I became curious about the cause of such pain and started researching the topic. I found that Harvard Medical School team has given one explanation for the brain freeze. They claim that the increased or decreased blood flow to the brain through the anterior cerebral artery, also called the vasodilation or vasoconstriction, causes the headache. Now I would like to test out this theory by drinking ice slush and keeping track of the pain from brain freeze and measuring the oxygen level changes in the prefrontal cortex. Because I wanted to see the brain in action during brain freeze, I did an experiment using a portable brain imaging system that utilizes functional near-infrared spectroscopy, also known as fNIRS technique. fNIRS detects the hemodynamic changes in the prefrontal cortex area by emitting near-infrared light into the brain and detecting the light intensity changes due to the oxygen level in the brain. My hypothesis is that if there are vasodilation and vasoconstriction in blood flow, which would result in oxygen level changes, this can be detected by the fNIRS device at the time of brain freeze. In the video, the participants will raise their hands when they feel the pain from brain freeze. At the same time, the fNIRS device will show the blood flow and oxygen level changes in accordance with such time period. And from these two, we will try to determine whether the correlation can be made between brain freeze and vasoconstriction and vasodilation. The purpose of this experiment is to verify whether the fNIRS device can detect a brain freeze by measuring the rapid increase in blood flow through the anterior cerebral artery into the brain, where the rush of cold blood causes blood vessels to dilate and produces pain as these vessels first open and then close. The subjects are a 45-year-old female and an 18-year-old female. So in this experiment, the subjects would be drinking a cold beverage with an fNIRS device put on the forehead to look at the changes in the oxygen level in the brain. Both subjects start with their brains showing the baseline, which is the color white. As they drink in the icy slush, the brain turns slightly blue. Shortly after drinking ends, the brain turns yellow to red. When the subjects raise their hands to signal their headache, the brain turns profoundly blue for an older subject and somewhat blue in a younger subject. Following are the findings from the experiment. The brain turns slightly blue when the subjects are drinking icy slush, suggesting that vasoconstriction occurs while the subjects are exposed to coolness. The autoregulation system then seems to engage sometime after the cold drink, since an increase in blood flow from vasodilation is detected as the brain turns red. Both subjects felt pain after the vasodilation and then slight vasoconstriction persisted, which can be inferred from the fact that the brain was in blue color. However, the subjects did not feel a headache under such consistent vasoconstriction. Despite the similarity of the overall tendency of change in the brains of the subjects, the reactions to cold drink did show interpersonal differences. From this small experiment, we were able to conclude that there is a chance that changes in blood flow from vasodilation or vasoconstriction are not the direct cause of the headache known as the brain freeze. The degree of acute vasoconstriction right after the cold drink was never severe as compared to that of persistent vasoconstriction after the exposure to coldness. In addition, the degree of vasodilation due to autoregulation was not unusually high as compared to what we intentionally create easily There are various actions such as the Valsalva maneuver, which indicates that the vasodilation itself cannot be the direct cause of the pain either. We seem to experience brain freeze only when the sympathetic nerve system alerts the autoregulation to start. Consequently, my hypothesis is that the brain freeze is related to the pain threshold of the sympathetic nerve system, to the coldness, and the changes in blood flow, which is known as the main cause of the headache, are just the byproduct of the exposure to the coldness. Thank you for watching.